Hi future scientists, I am Atom. In this video we will discuss collision theory and the factors that affect reaction rates. So what is collision theory? Collision theory explains how chemical reactions occur at the molecular level. According to collision theory, for a reaction to happen, 1. The particles must collide. 2. But it is not just any collision that will do the trick. The particles need to collide in the correct orientation. If the orientation is not right, the particles bounce away from each other. And 3. The particles need to collide with enough energy. For example, during a lightning storm, the air heats up sufficiently to energize the nitrogen and oxygen molecules to cause them to react to form nitrogen monoxide. Activation energy. Striking a matchstick is an example of the concept of activation energy. The friction from striking the match provides the necessary activation energy to start the initial reaction. Without this energy input, the chemical reactions in the match head would not occur because the molecules would not have enough energy to overcome the energy barrier, which is the activation energy. So activation energy, EA, is the minimum amount of energy that reactant particles need to collide successfully and start a reaction. It is like a hurdle they have to jump over. If they don't have enough energy, they won't make it over the hurdle and the reaction won't take place. Reactions with the lower activation energy happen more easily because the particles can get over the barrier with less energy. But if the activation energy is high, particles need a lot more energy to make the reaction happen. It is similar to climbing a short hill in your local town in a few hours versus trying to climb the Mount Everest, which will take a very long time. Imagine two people trying to give each other a strong high five. They need to aim their hands correctly and use enough force to make an effective high five. If they miss or just lightly tap, it is an unsuccessful high five. Similarly, if molecules don't collide with the proper orientation or with enough energy, no reaction will occur. Factors that affect reaction rate. What is reaction rate? The reaction rate refers to the speed at which a chemical reaction occurs. It tells us how quickly the reactants are transformed into products, or how quickly the concentration of the reactants is decreasing and the concentration of the products is increasing. So what can affect the rate of these reactions? Let us look at a few key factors. Temperature. When we increase the temperature, particles move faster because they gain more kinetic energy. This means more particles will collide with enough energy to overcome the activation energy barrier, increasing the reaction rate. When baking bread, placing the dough in a warm environment accelerates yeast fermentation because the yeast cells gain more kinetic energy. This increased energy leads to more frequent and energetic collisions, producing carbon dioxide faster and causing the dough to rise more quickly. On the other hand, refrigerating food lowers the temperature, which slows down the movement of particles and reduces their kinetic energy. This reduction in kinetic energy leads to fewer collisions among bacteria and other spoilage-causing microorganisms, thereby slowing the chemical reactions that cause food to spoil. Cold-blooded animals, such as reptiles and amphibians, rely on external temperatures to regulate their body heat, causing their metabolic rates and reaction rates to fluctuate with the environment. In colder temperatures, their metabolic reactions slow down, while in warmer temperatures, these reactions speed up. Concentration. In solutions, a higher concentration means more particles are packed into the same volume. This leads to more frequent collisions and a higher rate of reaction. On the other hand, a lower concentration means lower rate of reaction. For reactions involving gases, increasing the pressure packs the particles closer together, again leading to more frequent collisions and a faster reaction rate. Burning wood in air versus pure oxygen. When burning wood in normal air, which is 21% oxygen, the reaction proceeds slowly because there are fewer oxygen molecules available to collide with the wood. In pure oxygen, which is 100% concentration, the number of oxygen molecules increases significantly, leading to more frequent collisions and a much faster reaction rate. Cooking in a pressure cooker versus an open pot. Cooking beans in an open pot at standard atmospheric pressure limits the boiling temperature of water to 100 degrees C, resulting in a slower cooking process. In a pressure cooker, the increased pressure raises the boiling point of water to about 120 degrees C, allowing for more efficient heat transfer. This higher temperature and pressure cause the food to cook much faster compared to cooking in an open pot. Surface area. Breaking a solid reactant into smaller pieces increases its overall surface area, allowing more collisions to occur at the surfaces. This also speeds up the reaction. For example, dissolving sugar cubes. Breaking a sugar cube into smaller pieces increases its overall surface area, allowing more sugar molecules to come into contact with the water molecules. This results in a faster dissolution process because more collisions occur at the surface, leading to quicker mixing and dissolving of the sugar in the water. Calcium carbonate and hydrochloric acid reaction. CaCO3 plus 2HCl gives CO2 plus H2O plus CaCl2. Breaking calcium carbonate into smaller pieces increases its overall surface area, facilitating more collisions with the hydrochloric acid molecules. This accelerates the reaction rate, leading to faster production of carbon dioxide gas, water, and calcium chloride, therefore increasing the surface area of the solid reactants enhances the efficiency of the reaction. Catalyst. A catalyst is a substance that speeds up a reaction without being consumed by it. Catalysts work by providing an alternative pathway with a lower activation energy. This makes it easier for the reaction to happen. With the catalyst, more particles have enough energy to overcome the activation energy barrier, resulting in more successful collisions and a faster reaction rate. Catalytic converter in automobiles. Catalytic converters contain catalysts like platinum, palladium, and rhodium that speed up the conversion of harmful gases into less harmful ones. These catalysts provide an alternative pathway with a lower activation energy, allowing for faster chemical reactions without being consumed themselves. As a result, catalytic converters help reduce emissions from vehicles, making them essential for environmental protection. Enzymes. Digestive enzymes like amylase act as biological catalysts that speed up the breakdown of food, such as converting starch into simpler sugars. By providing an alternative pathway with lower activation energy, they make digestion more efficient without being consumed in the process. Without digestive enzymes, digestion would be very slow and inefficient. Food would take longer to move through the digestive system, and the body would not absorb nutrients well, causing digestive discomfort. While some breakdown might occur due to the acidic environment in the stomach and the action of gut bacteria, it would not be sufficient to meet the body's nutritional needs. And there you have it, the collision theory and the factors that affect reaction rates. Remember, it's all about getting those particles to collide just right and with enough energy. If this video helped you with your learning, please give it a thumbs up and share with other students and subscribe for more science fun. Happy learning. Thank you.